Thanks. Can you hear me? Yeah, great. So we start from where we stopped yesterday. And remember that yesterday we were trying to compute the curvature of the connection that I defined. So remember that I defined this object, this covariant derivative, that is an operation that I do to my correlation functions to obtain correlation functions of a deformed CFT. And we still have to find a way to estimate or compute this object here, the commutator of the covariant derivative. And we want to see if this is in general 0 or not, to see if this connection that is implicitly defined by this operation is trivial or not. And remember that I want to compute this as an operator acting on my space of fields. So I want to compute the components of this curvature. And remember that I try to convince you that this is some operation that should look like this. So this is the meaning of the left-hand side as an operator. And while this particular expression, at the beginning of yesterday's lecture, we didn't really know what it meant. But via the state operator map, I convinced you that the right way to ensure that these derivatives act only on one of the two operators is by integrating the marginal operator only on a unit disk. And I use the state operator map by thinking, remember, I think of a sphere, and I cut it at the equator, and I think of my states as defined on this equatorial circle, and this would be my ket, and my bras are defined on the other hemisphere. And after Neil's lecture this morning, I hope that this picture is even more credible to you. This is really the same state operator correspondence, but instead of doing very abstractly, I'm giving it a very precise quantitative coordinate expression, right? So then you will believe me if I tell you that the expression of this particular object in terms of integrated correlators is just, well, we have the standard 2 pi I squared, and then I have a double integral. So two O I O J, sorry, y1, y2, and phi k 0. This is supposed to be y1, and I have the commutator here. So this is the expression. I haven't specified where I'm integrating this. And now, if I were integrating over the entire complex plane, then remember this would correspond to having these covariant derivatives act on the entire two-point function, not just on one of the two operators, and we argue that that's 0. But the fact that this acts only on one of the two operators is implemented by restricting the domain of integration of these two operators on the unit disk. All right? So this is our formula for the curvature in terms of integrated operators. And now we have to, again, worry about divergences and all that. And I gave you a prescription for this. But before we worry about divergences, let's look at this formula. And we can notice immediately that if there weren't any divergences, then this thing would be manifestly 0. Why? Well, because in a correlation function, the order of the operators doesn't really matter. So I can always bring in this anti-commutator. So maybe I should write this anti-commutator explicitly. O I just to have maximal clarity. This is y y1, j at y2, minus j at y1, I y2. So you see that the only difference between these two things, if I'm allowed to commute the operators, is that one operator is complete. The OI here is computed on y1, and here is computed at y2. But the domain of integration is completely symmetric in y1 and y2. So I can just change variables, exchange y1 and y2 in one of the two expressions. And this would give me 0. Convinced? So the fact that if this is non-zero, it's entirely due to these short distance singularities that we talked about yesterday. So what is the meaning of this? So the order of integration now is very important. You see that I have first to perform the integral in y2. And when I integrate this operator over the unit disk, I have to worry about the singularities coming from this operator hitting the operator at the origin, as well as the singularities of this operator hitting y1. And then when I perform the second integration, I only have the singularities of the remainder. So first I do the integral in y2. I remove the divergences in the way that I described yesterday. You expand this you remove disks of size epsilon, you expand in powers of epsilon, you keep the finite part. And only after you did this, you do the integral in y1. You do the same thing, you worry about divergences, you cut disks, you remove the divergences, and you keep the finite part. This has no reason to commute, this operation in y1 and y2. So this, in principle, will give us some finite contribution. And let me say something, a simplification that occurs. You can study the OP of this particular combination. And some of you did it in the tutorial today. And if you study the OP of this, you will realize that there are no dangerous singularities. So the singular term in these OPs that would give a divergence in the integrated operator do not appear, can't appear. I encourage you to do this exercise because it's a nice application of the things that you've seen so far. And you just need to figure out what is how to invert an OP. It was already done in one of the lectures for the stress tensor or the current, or the OP between stress tensor and current. And you just try to do it with a general operator, and you will see that there is no danger of singularities from this particular thing. So when I regulate this, the only disk that I have to cut is around the origin. So just to make this procedure very explicit, so let me call Gij, y1, y2, this particular 4-point function. It's just the integrand. Right? Just notation. And then you have to perform the integration in y2. Y smaller than 1, but also y greater than epsilon of Gij. And then you have to subtract singularities. Singular in epsilon. And this defines for you some Hij. Well, there is always this 2 pi square. Well, it doesn't matter where I define it, right? So let's say that Hij is defined like this. And now, sorry, let me be explicit. This is just a function of y1. This is y1 and y2. And notice that I didn't have to restrict my integration to avoid the point where y1 goes on top of y2, or y2 actually goes on top of y1 because of this result here, that there are no singular terms coming from the OPs of the marginal operators themselves. And when I have this, I have to do the integral of j y1. And again, you can check that this, well, this is still on a disk of radius 1. And you will have possible singularities coming from the origin. So this is greater than epsilon. And then you remove singularities in epsilon. And you find your curvature. J, sorry, let me write it a bit bigger. Fij KL. I guess there is a 1 over 2 pi squared that I should put here always. All right? So this is your, and of course, when I say you remove the singularities in epsilon, I'm implicitly telling you to then send epsilon to 0. You only keep the finite term. I hope it's clear from the expressions that I wrote. Just a bit awkward to always have to say the same thing, but so you remove the singularities and then you send epsilon to 0. So if you want, I could have written here limit epsilon goes to 0 of the right-hand side. That's your procedure. So it's a very concrete procedure. And I hoped to be able to give it to you yesterday. So one of the exercises that I proposed is to actually go through with this computation. And if you do it, you will find this result here. I write. Okay, L. We'll find that this is, so first of all, I've been a bit cavalier with the spins, but let's reinstate the spin dependence. So you will find that, first of all, this is zero only, non-zero only if the spins of the operators that I'm computing the curvature, the components of, are the same. Then there will be a sum over all the operators in the theory, but it's restricted to all the operators whose conformal dimension is different from delta k. And let me actually do this. This is equal to two things. So, two cases. One is this, and it gives you, then have a delta as m, or maybe this is small, but okay, let me write it now. As k, c, I, k, m, c, j, m, l, antisymmetric here, divided by delta k minus delta m squared with a minus if delta k equals delta L and 0 if delta k is different from delta L. Can you read the symbols that I wrote? So just to be sure, let me spell them out. So this is a Kronecker delta. These symbols are the spin of the k operator and the spin of the L operator, telling you that this particular curvature is diagonal in the spin space of the components associated to these components. Then I have a sum. The sum goes through all the operators in the theory, but only those operators whose conformal dimension is different from the conformal dimension of the operator k. In the first line, the conformal dimension of the operator k is equal to the conformal dimension of the operator L. Here I have an additional spin restriction the spins that I'm summing over are also equal to the spin of the one of the two operators, Sk or Sl. And these are the structure constants. This is C, I, K, N, C, J, N, L, and I'm taking the antisymmetric combination. All right? And this is delta K minus delta M squared, which is all right because I'm restricting the sum here. And if the two conformal dimensions are different, I get 0. So, yeah, so there is a question here.
Sorry, just to be sure, so you say the sum is really for all operators, like primaries, descendants, everything.
Yeah. So strictly speaking, I derived this formula where where phi k and phi l are primary operators. Thanks for asking because I didn't spell it out. But the sum here is over all the operators in the theory, primary and descendants. I'm not exploiting conformal invariance to make the sum only go through the primaries. But you could do that. Probably you will get an even nicer expression. Yeah.
So why do you know that this expression converges at all?
Very good. So the question is, why do I know that this expression converges? And I do not know. But I will very quickly now show you a different derivation of this. So I can get away with not showing the derivation and leaving it to you as an exercise, because I will give you an alternative derivation of this formula. And this derivation will be based on the Berry curvature derivation. And even in standard quantum mechanics, the curvature of the Berry connection is not necessarily convergent. Let me just say that when there is supersymmetry, this sum has been computed. So when you have enough supersymmetry, so in particular for n equals 2,2 in 2 dimensions, n equals 2 in 4 dimensions, you can do this sum when these operators are chiral. That was one of the goals of this lecture series, was maybe to derive this, but I will not have time. But in those cases, you can do it, and this thing collapses to a finite sum. And this finite sum allows you to solve that subsector and derive all this, all the dynamics of the chiral subsector of the theory. So it's a very interesting story. So right now, it would seem a little bit of a useless expression. I just write it to show that this thing has absolutely no reason to be vanishing. But in a specific theories, computing this will be very difficult, and especially the convergence is not at all clear. When there are cases where this has been computed, and this has led to a very nice story. Maybe you heard all these TT star equations from Cecotti-Vaffa, and then some derivations are basically the computation of this particular curvature for supersymmetric theories in 2, and it was also in 4 dimensions. So that's all that I'm going to say about that, unfortunately. But yeah. So I want to also stress that this 0 is also very important, because it means that this connection that I'm defining doesn't mix operators of different conformal dimensions. So it's a very nice connection. It's unitary, as we saw, and it's also compatible with, it doesn't change the conformal dimension. And now I will show you what is the physical meaning of all these words. Because, you know, this is abstract, and all this formalism really shines when you can actually compute these things, and you can do something with it. And since I have no time to do that, let me instead show you what this means physically. And what I say, when I say physically, I really mean in a thought experiment. And so let me now talk about the Berry phase, or Berry connection. So I will slightly change gears very temporarily to talk about this topic, and I will show you how this is connected to what I say. And actually, we show you that this is exactly the same thing. So what is the Berry phase? Or I will talk about the Berry connection more precisely. So imagine that you have a Hamiltonian system in quantum mechanics. So a Hamiltonian system is just giving you a Hamiltonian. But a Hamiltonian, since we are doing, parameter dependence things, and we also let this Hamiltonian depend on some parameters. So this is a family of Hamiltonians that depends on lambda. And let's imagine that we are very good and we can diagonalize this Hamiltonian for every value of lambda. So we have a basis of eigenvectors. So this will depend on lambda. The energies will depend on lambda. So this is the meaning, right? I left some space to allow for possible degeneracies in the spectrum, which I just indicate with a little letter A. And now we ask the following question. We ask, imagine that I start my system at time equals 0. So let's say that I have time equals 0. And I choose an energy eigenstate. I say choose NA, just my choice. And then I imagine the following thing. So this is my lambda parameter. I imagine that I choose this particular eigenstate for a specific value, lambda 0, of my parameters. And now let me put lambda 0 here, because it's convenient, at the origin. And let's imagine that I now start to change the parameters of the system. This is something that you can actually do in labs. You have some external parameters that you can manipulate many times. And you can change them and do variation in the space of parameters and go maybe to another value of the parameter, lambda 1. And we try to understand the dynamics of this system as I change this parameter. So the dynamics of this system will now be extremely complicated because I have to solve the time-dependent Schrödinger equation. So I have psi t. I will have h of lambda, but lambda I'm giving it a t-dependence itself. So this equation is very complicated to solve. However, there is a drastic simplification that happens when I do this change very, very slowly. And what does it mean, slowly, very slowly? In practice, it means slowly compared to the typical energy separation of the various eigenstates. So if I do this change sufficiently slowly, so if lambda dot is small, well, 1 doesn't really make sense, but like probably 1 over En minus En. If I do this, then I have a very powerful theorem. It's called adiabatic theorem that tells me that the system will remain in the instantaneous eigenstate of the Hamiltonian. So there will be no energy transitions between these states, and n will not go to another n. The system will remain in the same energy level. It will continuously remain in this thing. Is it at least intuitively clear that this is what happens? Because there could be transitions, but transitions will be suppressed by a factor of this type, proportional to the time derivative of this thing. In particular, if I don't vary the parameters at all, the system doesn't change eigenstates because it's diagonalized. And if I change it very slowly, the energy state will change, but will remain in this n. So this is the adiabatic approximation. And it allows me to solve the dynamics almost completely. So it tells me that psi at times t will be given by, well, sure. I told you that it will remain in instantaneous energy eigenstate, but I should have said eigenspace. So the adiabaticity only disallows transition between different energy levels. But of course, the system might mix with other energy levels of the same energy. So there will be, in principle, some matrix here, which, of course, is unitary. So it will not be an A, but it will be some unitary matrix. And this also depends on T. And that's all that can happen. Did I write it in a? Yeah, I'm being a bit. The A is really here. Maybe I should, I don't know, put a label here that this. It's a choice. I chose A, right? Yeah, it's yeah. This carries the A. It's just the initial choice for my energy eigenstate. Right? What is this unitary matrix? Well, you can actually compute it by just plugging this inside this equation here. And if you do so, you will discover the following thing. First of all, let me also factor out a phase here, which also depends on time. And you will see immediately why I do this. So the phase that I factor out is just the standard evolution. So it's this thing. This is just the e to the IET factor that you get. But in this case, the energy is also changing with time. So it's an integral from 0 to t. This you always have, is standard dynamical factor. But then you can also solve for the matrix U. And the matrix U will be given by the path order exponential of this object for lambda 0 to lambda 1. AI. So this is a matrix where I introduce this object AI, which is also a matrix, and well, this is D or D lambda I. All right. So, yes, this question.
So you're somehow assuming that the dimension of the degenerate C doesn't change, but in general, if I start with something very symmetric, then this.
So a very good comment is that I'm assuming here that the degeneracies are not changing as I vary my parameters. It is an assumption that I'm making. If I don't make this assumption, I can still go through this procedure, but I will get a more complicated answer. In particular, I will have new effects like monodromies or other things when energy levels cross or when the degeneracies are split. And I actually did the same thing implicitly in conformal perturbation theory because I'm assuming that the degeneracy of my conformal dimensions is not changing with lambda. So basically, all that I'm doing is the generic point, is the generic theory evolution. Then there will be special points. It would be very nice to discuss this, but there is no time. But bear in mind that this is the generic thing, and then there are special things that need care, and we'll introduce new effects. So now let's read this. This is just the path order exponential of the line integral of this object AI, which I claim is a connection. And you can check very easily that this guy here does transform as a connection. And this is called the Berry connection. So you see, it's a very nice thing that the adiabatic evolution has defined for me a natural connection on my space of states. It's the connection that controls the mixing of eigenstates as I do an adiabatic change of my parameters. In particular, notice that if I had done a cyclic change in my parameters, I do a loop, then this will just compute the holonomy. So if this is equal to lambda 0, I do a little bit of loop, then I will have this loop integral. And you can recognize this from your fiber bundle courses or whatever, and this is just the expression for the holonomy of your connection in a principal bundle. So this is a unitary connection defined for you by adiabatic evolution. That's a very physical thing. You can measure this. This has been measured. This is also very useful to classify topological state of matters. This has been used to study things like quantum Hall effects. It's really a lot of applications. But it's as physical as it gets. And now I want to convince you that this connection is exactly the same that we defined before. Or rather, this is a bit of a less general definition, right? Because this is a connection on a space of states. And what I define is a connection on a space of all correlation functions, all operators. But remember that thanks to the state operator correspondence, the connection that I defined before induces also a connection on my Hilbert space. And how will I do it? Well, first of all, this is a connection given in components. So I chose a basis of my Hilbert space and all that. And from this, I can define a covariant derivative in the usual way, one that allows me to take derivatives in a covariant way, right? So if I apply this derivative, just the normal derivative here, this particular object will not transform covariantly, right? It will get a gauge shift, right? This object transforms as a connection, not as a tensor. But if I use the covariant derivative, then it transforms as a tensor. And now I want to compare this particular object to the one that I defined before. So remember that I told you how to compute things like phi k, phi l, ai, sorry, delta I, phi k. This we gave a very explicit expression. I told you that is the integral on the disk of all I, phi L at infinity, phi k at 0. And you can do this. And first of all, maybe since time is running very fast, let me not do it at the blackboard and suggest it as an exercise, but now you have all the tools to do this. So if phi L and phi k have the same conformal dimension, we did this exercise yesterday. But instead of integrating between epsilon, the ball that I have to cut, and 1 over epsilon, the ball that I cut at infinity, here I stop my iteration at the unit disk. And what I get will be a log of epsilon, like yesterday, from the lower bound of the iteration. But the upper bound of the iteration will be just log of 1, which is 0. So this thing will be 0 if delta k equals delta L. So let's look at what happens on this side. On this side, you can do the same. N B delta I N A. And you can see that this object here that I'm subtracting is precisely designed to make this 0. Right? It's really 0. Yeah? It's a really, you get this minus itself. So first check, good. And you should also do this particular integral, dy, when phi left is not equal to phi, when delta k is not equal to delta L. So since I see that you don't seem super confident that I'm saying correct things or that what I'm saying makes sense, so let me do this explicitly maybe. So this would be Ci k L, then I have the separation is y2 plus delta k minus delta L. Right, this is this 3-point function here. And I can do this and I have to integrate this from epsilon to 1. So you do it, and you get probably, I would need to, I'm not sure about the sign now, minus something that is plus epsilon dependence, which I throw away with my regularization prescription. And just check the sign. Yeah. And of course, I have a spin also here in principle. If the spin of K and L does not match, then I have also an angular dependence, which is killed by the angular integration. So just to be precise, this also carries the Kronecker delta in spin. And on this side, well, on this side, this corresponds to MB delta I and A. But you see, if the energies are different, my connection here is defined as a unitary connection that only mixes states of the same energy. And therefore, this, to compute this, is just the normal derivative. And this is just a very simple computation in conformal, in standard perturbation theory that you can find in any textbook. And this is the result. I should raise some blackboards, I guess. Yeah. And all that I need to show is that this is equal to this, but it is, I guess, self-evident now if I interpret my conformal dimensions as energies, and this guy here will be just this 3-point function here. So all that I'm saying is that the structure is exactly the same. Do you see it? And the only thing that we need to understand is the relation between these symbols on this left side and the symbol on the right side. But this is obvious from the fact that we are doing radial quantization. And if you think about radial quantization, this is nothing else than the standard, the natural quantization that you have on the cylinder. So if you take the plane and you map it to a cylinder, then your evolution along the direction in the cylinder is equal to the dilatation operator on the plane. I think it was explained also in the other lectures. And so the Hamiltonian that characterizes your time of evolution on the cylinder is precisely the dilatation operator. So all the energies in radial quantization, when you go to the cylinder, are precisely the conformal dimension of the operators. The Hamiltonian is precisely the dilatation operator. So if you want in formula, H on the left will be what you call L0 plus L0 bar in standard, if you have the in terms of the Virasoro generators. And what is delta H? Well, delta H is the now integral of the marginal operator. But now we don't iterate over whole space because this is a Hamiltonian. The Hamiltonian is a fixed time concept. So I only iterate over time. Again, in radial quantization, this means iterating over circles centered around the origin, in particular circles of radius 1 in the conventions that I'm using. And so now it's evident that if I do this, if I want to compute this particular matrix element in this language, I just need to compute this integral here. But when I just do the integration over the unit circle instead of doing it on the unit disk. And this will lead me to precisely the numerator of this guy here. So what I've shown to you is that the Berry phase is identical, the Berry connection is identical to the connection that I define in conformal perturbation theory. And this would not be the case if I had chosen any other regularization scheme. So, well, if I had chosen a random regularization scheme, this connection would be completely broken. So I hope that this gives you another motivation to believe that this is the natural connection to put on our space of conformal field theories. I had promised to do something else, but I'm out of time. I had promised to justify that formula over there on the left. The thing is that when you have this formulation, you can compute the curvature of this connection by using standard gauge J, the standard formula. I might, the sign, this particular sign depends on the conventions. There might be a minus sign, overall minus sign to match it to my conventions above, I don't remember. But this is just the curvature of this connection as seen as a gauge connection. You compute it in Yam's theory all the time. You can really do this computation. It's much easier in this language. And trust me, you will find that formula over there that I wrote on the top. And I would conclude with this. Thank you. Yeah, questions?
So, is there also some sort of equivalent of this adiabatic theorem in the conformal perturbation theory setting that you're studying?
Right, so the question is whether there is a analog of the adiabatic theory in conformal perturbation theory. And I'm actually using the same adiabatic theorem. So I don't use any analog because what I'm doing is I'm mapping my CFT to a cylinder. And then I'm thinking of doing adiabatic changes of my parameters as my theory lives on the cylinder. So the difference in conformal dimensions in my spectrum of operators is what will control the adiabaticity condition. Of course, if I have a continuous spectrum, for example, like in Duville or other theories that are maybe more sick, well, they are perfectly fine, they are like more complicated, then I will have to use much more care. But everywhere, right? I mean, whenever I write sums over the OPE expansions, I need to write integrals. You saw it in the last lecture with Sylvain, and everything would be much more complicated. The adiabatic theorem has been generalized to continuous spectrum, but it works when there are gaps in the spectrum. So it's typically used for bands. So you have like energy bands in say a condensed matter setting, and you consider the projector on the energy band, and you think that the energy bands are separated by some gap, and then you study the connection associated to these particular projectors. I don't know if there is any analog of that in this language. Yeah.
How far can you sort of try and push this argument? Like, you could, it kind of looks like you could try to do this with
That's right. Right, so the question is how can I push this, how much can I push it outside of the boundaries of conformal field theory? And indeed, this equivalency between the two connections strongly suggests that all these concepts that I talk about should be generalizable well beyond conformal perturbation theory with exactly marginal operators. That's the hope. It's just that that was one of the motivations why we investigated this equivalence in more detail, because we have this hope that this allows us to say something about quantum field theories that are not conformal. There are not so many results at this point, but this is something that we are definitely thinking about. It's a hope. I share the hope with you. So.
Maybe quickly further to that question, what about CFTs in higher dimension?
Okay. So what about CFTs in higher dimension? Yeah, so nothing that I said depends on the fact that we are in 2 dimensions. Everything that I said, even most of the formula should be valid. For example, those formulae with the spins will be replaced with formulae with the higher dimensional analog of spin, like, you have spherical harmonics. And so this is really, it's not 2-dimensional by any stretch of the imagination. But in 2 dimensions, you have all these other technologies that allow you to prove things much more convincingly, like the conformal invariance of the deform correlators and all that. I'm not sure what happens in higher dimension as far as formal proofs go. But yeah. No question.
The equivalence between the 2 connections depended on the fact that the space of states that you have in the very phase context is equivalent to the space of conformal, the marginal perturbations.
Yes. Yes.
But that also depends on, that also is due to the state operator correspondence.
Mm-hmm.
So if there's no state operator correspondence, then the connection between the connections is destroyed.
Yeah, so the comment is the equivalence between the connection in conformal perturbation theory and the Berry connection, this really strict equivalence depended heavily on the state operator map, like the bijection, right? In a general quantum field theory, you lose one of the directions. And so how do you, so how general can you expect this to be? Yeah, it's a good comment. I don't have much to say about that. It's just a surface of attack that kind of opens up, but how much mileage you can get out of it is absolutely not clear. Yeah. More questions? Okay. Oh, there is some.
You mentioned in the tutorial, like, you weren't worried about second order because you could imagine that it would visit every point and do it order by order. But if I actually try to do some finite distance away calculation, say numerically, can I plug this, iterate this procedure many times and get some realistic faraway pointer?
Okay, thank you for the question, because I mentioned something in the tutorial that I had promised that I would mention here, but I forgot, as expected. So, so I will repeat the comment that I made in the tutorial first. I'm explaining this formalism, and all that I did was first-order perturbation theory. You might be worried about second order and all that. But notice that I described how to do first-order perturbation theory around a generic point. So one strategy to do all these computations to all orders would be instead to do first order and then first order around the perturbed theory. And then first order again. So you kind of, it's like describing a curve by specifying the tangent vector at each point in the curve instead of specifying an infinite number of conditions at the initial point. How would you translate all this formalism to maybe any order perturbation theory around a specific point? This is a very complicated question that, as far as I know, has no complete answer. You can look at second order perturbation theory, third order, and see how things go. And there are many complications. The nature of divergences becomes more complicated. Already a second order, you will definitely have higher logarithms, just like in standard perturbation theory, and so on and so forth. So it requires a bit of work. The question specifically was, can I integrate this connection, for example, numerically? Or, yeah, so this is one of the great features of doing things in this way and choosing this regularization scheme, is that this connection doesn't mix states with different conformal dimensions. So these connections can really be thought as so this connection on the space of operators really breaks down into finite dimensional connections on each subspace of operators of the same conformal dimension or the same energy. And that's integrable because it's a finite dimensional system. But if I had an infinite dimensional vector bundle with a connection that does not have this property, that doesn't split as sum of finite dimensional connections, then I will have a problem of integrability. And this is an actual problem that people encountered in the early days of this procedure when they were regularizing and renormalizing these correlators in a different way. And I would get maybe different connections, maybe even a flat connection, but this led to non-integrable connections. So yeah, you can, this connection is actually integrable, thanks to, so I imagine that you could do it numerically. There shouldn't be any problem if you have power. Yeah.
Okay, if there are no more questions, let's thank Marco. This was the last lecture, so let's give him a big hand.
Thank you.